I think Krishna, it's already 3 o'clock. Can we start?
Yeah, maybe, but we have only 50% of participants. So
Okay, we'll wait.
maybe we can wait a little bit.
Sure. Yes, Krishna, I think almost all the many of the participants are waiting.
Okay, ma'am, we can start.
Yes, because they have many works to do.
Yeah.
Also, they have to join by evening also, 7 to 10.
Yeah.
They have two guest lectures. Yes.
Yes, sure, definitely. Okay, so I'm sharing my screen. So actually, I can't share the screen. Actually, it's showing that host disabled participants sharing.
Yes. Now you can.
Okay. So I think now you can see my screen.
Yes.
Okay. So last time, like last session, we had completed the MBT ensemble, and now we will go for the NPT. So here, actually, already I have run the NBT because this is taking time. I think it is unnecessary to wait. So I will explain everything, and this is the maybe you can. Someone is, I don't know. I have not, maybe someone is writing something over the screen. Okay, so whatever. So here we can see that these files I generated from the NVT. So last time we ran it. So these actually
you can clear the drawings from annotate section. I think go to the top of your screen.
Okay, from where?
Zoom.
Okay. Zoom.
Some options will come like clear annotation. Yeah, Zoom app.
This one.
You go to your Zoom app.
Okay. So can you see anything?
Do you have any controls at the bottom of your Zoom panel, like security, screen sharing options?
Sorry, I can't.
So at the bottom of the page, I think. Share screen option.
Yeah.
Bottom.
How you have shared the screen? Just you share the screen from the bottom below options after opening the Zoom app.
Okay, I just.
I will. You share again. I'll make you host. That's fine.
I think now it's fine.
You can disable the participant. Okay, you can carry on.
Okay, so now we have the output from the NVT. So here we have given our system the temperature. So now we want to add the pressure and temperature as well. So as I told you, like you can generate series of NVT and NPT step as per your requirement. So for the tutorial purpose of view, I just want to give a overlook that, okay, these are the NVT and these are the NPT step you have to follow, but design your experiment by your own. So for the NPT step, you have to follow the similar kind of command, that is this. This is the command for the NPT. So you will take the output from the from the previous NVT step. So here should be NVT and NVT. So you will generate the TPR file, then execute. Then you will get the NPT TPR file. Then from there you will run the like similar way you will run the NPT step over here. So here also you can control all the parameters in the NPT MDP file. You can visualize it. NPT.
So Anil, do you have some question?
Yes, sir. My question is that in NVT we are going to heat the water, and in NPT, what we are going to do? We are going to increase the pressure of the system,
Yes.
and why?
Yes, because the system needs the pressure as well as temperature. It's just virtualizing, mimicking the realistic environment of the cell.
Is there a limit or something that we can go up to that pressure, or it's arbitrary?
No, actually, for the temperature, actually, you know the temperature of the system, where in which temperature you will run. For the pressure also, there is some value you can set, like here you are giving the temperature. So temperature is basically the isotropic kind of temperature, pressure you are maintaining. And actually I am unable to answer. Maybe Dr. Pratit can comment on this because he is expert in this pressure term. Is he here?
Oh, Rohit is here. Pratik is not.
Okay, so maybe he can answer, but I don't know.
Okay. Continue.
Okay. So here also I have. Sorry.
Can you repeat the question? Participant asking some question maybe.
Panwar, can you repeat the question?
Yes, sir. My question was that in NVT we are going to increase the temperature of the system, like that we are going to heat the water. water
Yeah.
molecules. And in NPT, does we are going to increase the pressure, or if you are going to increase the pressure, then what is the limit? Means we are going to 1 bar, 1.5 bar, or how can we justify that? How much we can increase the pressure of the system?
No, no, actually, see, yeah, MVT means volume and temperature, and PT means pressure and temperature. Temperature will in both NVT and NPT, and then the standard parameter is 1 point something is there. Okay, you have to check the Grover's
Here
tutorial
we are.
also, actually. But if you are doing in some different condition, or if you want to do 2 or 3 simulation in different pressure, but actually I don't think that changing the pressure is required, because the cell has a constant pressure, every cell. But if you want to change, so you have to read according that, and then you can define here in different parameters. These are the different type of parameters which you have to read firstly, that okay, if that, like here you can see that particle mass evolved method is we are using for long range electrostatic calculation. So you have to read what is the PME and what are other methods, and then you can use some other methods here, like for temperature coupling we are using Bedenson's thermostat. Okay, and this is the default. But if you want to change, so you have to read the things. This is the advanced molecular dynamics simulation actually. So you can change the pressure also, you can change the temperature also, you can change anything, because here different things, different type of things are written. Like if you want to change the temperature, so you can change here, like where 310 is written. Okay, you can change temperature here. So you
Yes, sir.
can change the things, but you have to read firstly that what they are doing and why we are changing the pressure. Okay.
Okay, sir. Thank you, sir.
So
Okay,
this is,
welcome.
thank you, Rohit. And this is, I mean, about the system, like what exactly you are going to do. And according to your experiment, you will plan the pressure and temperature basically. And the thing is like in the different condition and different experiment, the things are different. So you have to know your system and what exactly you are going to do. So based on that you will do it. So another thing I want to comment here is like we are giving temperature, like separate temperature for protein and separate temperature like again for the non-protein part. It's other than other than protein, you have like water and the your these ions are there, so you can just separate so that the temperature will be heated properly. And if you have some another like if you are going for the protein ligand simulation, so you can, it is a good practice to define the temperature group for the ligand as well. Okay, so from there you will generate the NTP file, and here, as I told you, like the time scale you will decide by your system, and
Amar is having some question. Amar, can you ask?
Sir, can I modify the MDP file?
yeah, of course. As I we all are discussing about that based on your system, and there are a lot of parameters, like lot of algorithm also there. So based on your system, you can modify. So you have
So
to
that is authentic for research on the authentic work. That will be authentic work.
Of course, like someone want to simulate his system in freezing temperature. Like some people are studying in protein, the freezing temperature, what is the protein, is the behavior of the protein. So you can, of course, you can change into the, less than 0 Kelvin. So based on the purpose of your study, you can, design your MDP file.
Okay.
Take the time.
Thank you. So after that, as I discussed about the position resistance. So here we basically up to the NPT step, we basically maintain the position resistance, and also it is also a good practice to run I mean, NPP step without restraint. Let's say I run some couple of nanosecond without restraint of NPT simulation. Then after that, that output file I basically take for the free simulation run. So this is one classical simulation, but we are doing. I have explained it here, and for that. Actually, we are not biasing our system. So if you want to address something like a protein folding kind of the problems, so this is not the you can run it, but it will take long time, let's say some years to get the protein folded. So but in the nanosecond scale, we can have some this trend, like how the things are going, and you can correlate your simulation with experiment. So now we will run the free MD. So for that, we will again we will use the same way, that we will take the input parameters and the output from the NPT and the topology file, and we will generate the NTPR file. Then we will run the similar way the simulation, the free MD. So here actually I have already run the simulation for 100 picosecond. So these are the file I have attempts, and actually you also get one log file in every step. You can see every step you will get some log file. In the log file, how your system is running in every step, you have all the information. So here you can get the information like what is the command you have used, and the systems, the processor, whatever you are using. Then for the this is the parameters, input parameters you have given, and for the each step information you are getting, like which which time scale and whatever the temperature, angle, but every information you will get in the log file. And you can also see from here the speed of the system. So here I just run in 4 CPU, so I'm getting like 2.5 nanosecond, something like that in a day. So here you will get the GRO file, MD GRO file. This is the coordinate file, the last coordinate file you are getting, and you will get one XTC file. XTC file is the trajectory. And let's say I want to prolong the simulation for a couple of more nanoseconds. So the command will something different. It will be like CPI APPEND. So you will again generate you will again generate the TPR file. Then you can prolong your system for same trajectory. You can prolong like more if you want to run for more a couple of nanoseconds, so you can just prolong in CPI append way, but you should have the CPT file. So the CPT file is the previous coordinate file you have, and also there is EDR file. This EDR file contains the energetical term. So basically a few people, they delete this EDR file. So these are really important when you are calculating some energetical term. Let's say this potential, for the potential energy, or some Lie, there is binding free energy if you are calculating like using the Lie method. So this EDR file really very important.
Anil, you have a question?
Yes, sir. My question is that we are using Gromax 5.1. Okay, sir. And in Gromax 5.1, XTC and .trr file they will make. But now I am using 2020 versions, 2020.1 version of Gromax. And in this latest version, no TRR file they are making. Only the XTC files are they are making. Do you know why it is so?
Actually, in the TRR file, everything is, this is also one type of writing the trajectory. But in the XTC file, basically, this is the compressed form. So actually, it is not recommended to generate the TRR file, because when you are running in microsecond or something like that, the TRR file will be generated on huge size of file, and it will just not necessary, because most of the information you can extract from the XTC file. This is a compressed form, like here you can see that the 100 picosecond file is only 4.9 MB, but the TRR file maybe it will be in something like 50 MB or 100 MB, something like that. So this is not you can generate, but we generally get all the information from XTC, so it's fine.
Thank you, Krishna. Continue.
Yeah. And you can use any version of the software, so that is up to you, and there is no limitation that okay, you are using this older version means something wrong or something. This is not like the case here. Actually, you can control everything from the MDF file, and from the the way you are designing your system. And also the force field. The force field is really important. So from there you can control your system. Basically, the Gromax has their codings and everything is the mother code which they have borrowed from Gromas, as I told earlier. And this is everything is similar. And the Gromas is, I think, written initially in Fortran. Then Gromax is written in C++, so that's why the Gromax is faster, and the version is not an issue. They just fix some of the bug, and also they have include and exclude some of the tools. So that is the only difference. So this is no issue of using older or newer version. So it is up to you what you want to use. And so now we all have completed the free MD simulation, that is the classical one. So now we will go for the analysis. Okay, so as in the in the lecture in the morning that we have heard that we have given some periodic boundary condition to the system, so that if, let's say, if your protein, I can show you just a minute. Okay, so this is the box, and I think everybody has a bit idea about the periodic boundary condition and what exactly is happening. This is a 3-dimension box. So this having the XYZ coordinate. So here basically the PBC means, the periodic boundary condition means, because this protein is moving inside the box, okay, and it might happen that some part of protein during the simulation may come outside the box, okay. So if that will be the case, then the problem is here is no, here we have no control of it will feel like a vacuum. There is no environment. So to to tackle this problem, scientists, what they have done, they have created a virtual environment using the PVC, like the extension of the box from here, and in every coordinate they have like one virtual box, so that if the protein will come out from the box, so that it won't feel like it is in the vacuum. So whatever protein will come out from here, that will be compensated from another side. Okay. So here also there is another issue. If just imagine that some part of protein will come here and some part will be compensated from here. So that may be a chance that the box size is really very little and it can interact with each other. So whenever you are making a box, so that making a box, you should make a bigger box. I mean, some people, they think that, okay, I will create a smaller size of box so that I will have lesser number of atoms, so that my simulation will be very fast. But you will have the problem that your protein may interact with same protein, like it will interact with itself. So there maybe the simulation will be completely wrong. So you should calculate the periodic the periodic image distance. There is a way to calculate the periodic image distance when you will do some advanced level of calculation, so that here you will know that what is the distance between the periodic image of itself, so that you can prevent this type of interaction, which is create some artifact in your simulation. So this will just error. You can prevent this error. So it is recommended to make a bigger size of box. Like in the tutorial, they have given like from distance, like from the protein, the box distance is 1 nanometer, but in this tutorial I have given like it is 1.5. So it is up to you how much bigger box you are making and how flexible is your protein. Let's say you are working with some peptides or some IDP generally. So at that time, the mistake what I have done, I have run like a 1 microsecond simulation for a IDP protein, and I was really very happy that okay, my simulation is done, but the trajectory was not, when I compare the result like J coupling and chemical shift with experiment, it was like large deviation. So I just thought that what is really happening. So I actually created like 1.5 nanometer distance box, but still the IDP is really very flexible. It was like jumping like here and there. It was coming outside the box, and it was interacting with itself. So my whole 1 microsecond simulation was completely wrong. So from there, I got an idea that, okay, so you should not, minimize the box size if your protein is really very flexible. So you should, take a little bit bigger size of box based on your protein. You will know that, okay, this protein is not that much flexible, and this is, very stable protein. So based on that, you will decide what is the box size. Basically, there is no such golden rule that okay, the box size should be this much. So this should be decided by the scientist who is working with the protein. And so that's why I first day I told you, like yesterday I told you, like you should know your protein, your ligand before you are going for any experiment here. Okay. So basically, here we add this PVC. So that's why when you are doing the analysis, you have to remove the PVC, then do the analysis, so that there will be no jump.
So may I ask a question?
Yep, sure.
Sir, I want to ask is there any website or something from where we can get the information whether this protein is flexible or not? Because in most research paper, I don't think people mention about the flexibility of protein. So from where we can get the information so
Uh,
that we can incorporate in our study?
Actually, this is the information is, I mean, nobody write in their paper, but this is based on your experience. Like you should know your protein first before going any experiment. So you should know that, okay, you are working with some IDP. This should be like very flexible and it may come outside the box. And if you're working with some cytosolic protein, this maybe you can have an idea that, okay, this protein is very intact and it's having a very one good conformation. So maybe it should not go outside, but nobody can say that. So based on hit and trial, you have to find it. And another thing I will tell that when you are running the simulation that, okay, so you generated one trajectory, so that is not enough. You should generate like 2 or 3 trajectory for the similar study. From there, you can compare what is the RMSD between this trajectory. So from there you should do the analysis and publish the paper, because as we discussed in the morning session, this is a stochastic simulation. So you should do it multiple times, like experimentalists, they do do the same experiment again and again and take the best one. So like that, here also you should go like this. So actually, yeah, in paper people don't mention, but it's a good practice.
Sudeep, you have some very.
Yeah,
Sorry?
am I audible, sir?
Yeah,
Hello?
you're audible. You're
Yeah.
audible.
So my question is, can B factors be a good point we can take into identifying the flexibility of the protein?
Yeah, definitely. That is also a good thing. Actually, B factor you can get from the PDB itself, and also you can calculate the flexibility by RMSF plot, which I will show you in the analysis when we will do the analysis. So where there also you can get the B factor, and based on that you can say the stability of the protein. So actually, maybe I can show you one of my paper. I actually calculate the B factor of the protein from the trajectory. Then I presented that you can color your protein in that way, that where you can say that, okay, this part is really very flexible part of the protein, and where is really very stable. So from the B factor also you can say that. Thank you. So maybe we can continue with the analysis. Okay, so as I told you, like we have to remove the PBC. So for that, there is a command that is called transcom. Transcom is a really very useful command if you are using the this GROMACS, because I mean, I can say you this is the beauty of GROMACS, that why people are very much using it, because GROMACS has almost all the the inbuilt analysis tool, and most of the simulation package they don't have. So that's why people really like GROMACS. So here, like you can already they have developed most of the analytical tools, so that you should not one should don't have to write the script like in the NMD. If you get the trajectory, every time you have to have your own script, or you have to depend on somewhere, or if you are a programmer, you can write script and do the analysis. But here you don't have to, like the tool is available. So you just have to know that correct tools. So that's why I stress always that you should know read the manual, so that from there you can get the information of the how to use one tool for different kind of problem. Like I can tell you the edit conf, whatever we use in the morning, that is really very useful tool, and that solve many problems. So you just have to know the correct, this correct flag. So you have to read them like, and you can't find them in any tutorial. So you have to educate yourself, knowing and reading all the flags, what one flag is doing. Like in the morning, I told you that this PDB to GMX command, that is GRO command, it also can handle if you have oligomers. Like people have a lot of problem with, like they want to study about the oligomers, and they can't generate the one GRO file from the from the oligomers, and when you will don't use the merge flag, it will generate like it will take one chain and it will generate the topology. So again, you have to go to generate another topology for another chain. But using the flag of merge, you can solve the issue. So like that. So there are so many things in GROMACS. You just go through each command and know how to use the flag, so that you can save a lot of time and the things. So like that, the transcom command is really very useful to convert anything, any format. Like in the morning, I told you, like from the GRO, we can convert into PDB, like using the transcom. Okay, so here you will remove the, remove the PVC from that from our trajectory. So for that, we take the input from the output of the last command, and the output is like here. I just name it like no PVC. Okay. So there is some problem. Okay. Let's see. Maybe I have some. Just a minute. I'm really sorry, because sometimes I am used to with my own script, so I don't run it like this. So maybe that's the. So I don't remember all the. So maybe Rohit can help. This is the TPR. We have the TPR, we have the HTC, and the
minus PVC.
Yeah, I have used the minus PVC. Okay. Okay, I just forgot to use the minus center. Okay, so here basically, in the strip trajectory, what exactly you want to take, based on that, you can select. Like here, you can select the whole system, or you just want to have your own only the protein, or you want to have like protein with some ligands or something. So for that, you have to make one index file. I will tell you how to generate one index file, and from there you can select. Like here, I just want to select only the protein, because sometimes when you are having like large trajectory and you don't need the other information other than protein, so you can use the only the protein, but you should not delete the raw file, because maybe when you communicate some in the publication, for the publication. So maybe some analysis need water or something else. So you should not delete. And also there is the new regulation is coming in for the simulation community that after publishing paper also, if maybe 5 years later, if someone will ask for the raw trajectory, you must have to give. Otherwise, maybe your paper will retract. So these rules are coming in the Europe and US. So maybe in India also will have like a similar kind of role for the computational people. So please don't delete anything from the raw data, because there is very good way, like very easy to manipulate the data. So the authors, someone will need your trajectory. So you should not delete anything, the raw data. So, okay, so now we have generated the strip trajectory like here. And now we will go for some basic analysis like RMSD. So for that, you will go to the RMS. There is one RMS command. And if you are using the lowest version, like this is like GRMS, something like that. Okay, so we will use and okay, so this is the command for RMSD. So basically we are taking the force field parameters, then the trajectory, then the TUNS is the flag for like if you, by default it generate in picosecond F, and if you want to know, get your this graph in nanoseconds, so you can write TUNS so that it will generate in nanosecond. But here our trajectory only 100 picoseconds, so I will not generate. Yeah, actually for your purpose, actually I have given you 1 nanosecond this file, this XTC file, so that you will have feeling that okay, so you have 1 nanosecond trajectory. And also I have stripped only the protein, I think, for the 100 nanosecond, but the original simulation was 500 nanosecond, and we communicate, it published in March. So there is
here -O and something -O RMSD output for that one, and here
actually sorry, no,
-F -S.
Yes, yeah. Actually I changed. Actually, as I told you, like I don't remember. Actually, you don't have to remember this thing. Actually, I use the script so that I don't remember the commands. So you actually, nobody has to remember the command. All the commands is in the tutorial, and also you don't have to remember this thing. And also with help, you will have everything, all the flags. So you don't have to. So here you will decide which RMSD you want to calculate, like a protein or the C alpha or the backbone or whatever. So okay, you can choose based on that, and you can have the RMSD of thing. So let's say I will choose the backbone RMSD. So here you generate, we got the RMSD of. So if you open this file, here is like the RMSD plot. This is the thing, and you can plot it like using any tool like Excel or whatever you like. So basically I use XMGrace, that is really very friendly with GROMACS, and actually GROMACS generate the XMGrace format file always. So you can use that. So you have to install XMGrace like this, and you can plot it. So do you have any questions? Because it will take some time. Actually, it should not take time because my terminal is in Europe, and I'm using through the remote machine. So that's why it will take some time. Yep. Yep. So this is the RMSD plot for the for our simulation. So like this, you will get the plot for the publication. So if you are using the XM grace, so from here you can manipulate everything. Like actually, it will be very slow. So I don't know. I can show you. Like if you will click here in the x-axis or y-axis, so you can manipulate the x-axis and y-axis. If you want to calculate the average error, whatever, so you can calculate over here, or you can use any any tool for beautiful graph. At the end, actually, you need some kind of beautiful graph for your publication. Okay, so now we will go for another calculation. So actually, as Rohit was telling, that you need to give something else like output. So actually, I don't give, because this is like by default it generates, so we don't need it. And it's like, but it is a good practice to give proper name. But here actually, for the tutorial purpose, we don't need any sophisticated name or any particular name for that. So RMSD is fine. So that's why I didn't give the output name. So here you can do lot of stuff. Just you have to go through it, and if like each flag, what exactly they are doing, and from here you can get many things. Like for example, like someone want to plot it like some XPM format file, and some beautiful more beautiful figures. So he or she can generate the XPM format, or some using like dist, you can generate like other thing. So like that, there are several things you can calculate. Just read them and use it with your purpose. So now we'll go for this is the RMSD, as Dr. Pratis has already explained in the PPT. So now I don't want to explain it again. So this is like the RMSD will give you the overall protein, like for the each frame, how how much the RMSD between the initial frame. So it will generate one time versus RMSD plot.
Yes, Anil sir, can I ask?
Yeah.
Can I see the graph, RMSD graph again, sir? I have a question regarding that.
Okay.
Okay, if it is taking time, then it's okay. My question was that during the mid of the graph, like that 0.6 to onwards, the RMSD increasing, and sometimes the reviewer said that if the RMSD increasing at the last, you must increase the time of your MD simulation, means till the system is not stable RMSD. Is it okay, sir?
Yes. Actually, you want to get the converse of the simulation, so that you want some linear curve, so that you will know that okay, after certain time it will converge, so that you'll have a stable RMSD. So from there, you can say that, okay, my system is converged and there is no need to run it further.
Means in this graph, we can say that after
Yes.
0.5, the RMS increasing, so we must increase our MD simulation time.
Yes, exactly. Actually, for the tutorial purpose, if you actually, I just run only 100 picosecond.
Thank you, sir. Thank you.
So maybe I will show you how it looks. When it is for the 500 nanosecond. Here you can see up to the 500 nanosecond. This is how it looks. So here you can see some linear curve, so that you can know that, okay, this my simulation is converged. So like if I prolong, so again I will get similar kind of curve. So there is no need to prolong it.
Hello, sir. Hello.
Hello. Yeah, you can.
Yes, that graph you were showing just now. What are those green, red, and black lines showing?
Yeah.
Green, red, blue line. What are the different lines showing here?
Okay, actually, what I have used, like here, I have used two type of force field, that is umber and also the gromus, and I have a comparison between the two of them. And for the black one, it is the apoprotein, like without ligand, and the red one is umber with ligand, and the green one with gromus apo, and the blue one with gromus, with ligand. So these are the curve.
Why do you have used the two different force field for different conditions? What was the basis?
Actually, the thing is, you can also visualize that here using the two force field, you have like two different kind of plot. So when you are going for the drug designing purpose, we should not believe only one force field. We should compare the result with the different force field, so that we have an idea that, okay, so I mean, this is drug design is very sophisticated, and it is life-saving thing. So that you should not like, okay, I have just run one simulation and I will just communicate like, okay, this is doing, or maybe in some other force field, you will get some another result. So the ligands is not that much good, but here we have compared the two force fields, so that here we have a idea that, okay, these are converged and this protein is not getting out of it, and we have like similar kind of trend, so that we can say that, okay, this drug maybe further we can go for experimental study with this drug, because this is computational and we should not believe only one force field. So this is the idea between doing with two different force field. And also you are you should very careful while choosing the force field, because first of all, you have to know the equation of the force field and what are the points your force field is lagging behind. So based on your problem, you should choose the force field, and you should always do the literature survey and also see the benchmarking paper. So there are a lot of benchmarking paper, like people do a lot of simulation and benchmark between the force field, because if you go to only the force field paper, let's say I will go to Umber or Gromas force field paper, and I will say that all the force field people will say that, okay, our force is the best, but you are not the developer, we are like users. So how you will trust someone else? So always follow the benchmark paper, like for the certain kind of problem, what is the benchmark paper is saying? Like people are doing the benchmark with different kind of force field for the certain problem. So from based on that, you'll have the idea, okay, my problem is like that, like the benchmark paper. So from there we can just trust that, okay, this is the thing. And you can always, if you have some experimental data, always validate with that, so that I mean, this work should not be like novice or something. Okay, so So now you want to see that the fluctuation with its amino acids. For that, you calculate the RMSF plot. So only the change is RMSF. You will everything is similar, and here another flag you will use that RES. So if you don't use the RES, it will give you, I mean, the legend of the plot will be like atoms. So but I don't like that way, so I use the res command, so that it will give you I mean, for the each amino acids, but there is no difference, only the legend will difference. So here, again, you can choose whatever you like. Let's say I will choose the C alpha. So here again, you have the RMSF. You can check it, and it will give you the RMSF of each amino acid, so that you can say that, okay, from the locally this part is flexible and this part is not flexible. And also I will show you how to get the plot for the B factor.
Sir, may I ask a question, sir?
Sure.
Sir, just like that, we have chosen that RMSF for second options, that alpha, because most of the time we select the whole protein, the second choice two. Is there a difference between choice two and choice three? Means whole protein or carbon alpha at the RMSF?
Sorry, actually I can't get you. Can you please repeat?
Yes, sir. When you just enter this command for RMSF, you select the point 3. At the point 3, there was the carbon alpha, RMSF for carbon alpha. At the point 2, there was the protein, whole protein. Most of the time, as we saw in tutorial, we calculate the RMS for the whole protein. So my question was that, is there a difference between the RMS of whole protein or RMS of alpha carbon?
Of course, it will be the difference, because here actually you are calculating only the C alpha, and there is something. I mean, along with the C alpha, there is the side chain and also the whole protein. So of course, it will be the difference. But actually, the thing is, I like to calculate the RMSF of the C alpha. So that's why on most of my paper I basically use. So you can also calculate for the proteins, there is no problem. So that is up to you what exactly you want to present.
And my second question is said that when we see the graph of RMS, the tail ends means starting and end of the protein, it will hike like that, get RMS. And most of the graph I see that is that the ends of the proteins, they are okay. It's okay in your graph. Okay, it's okay in your graph. But when you show your last graph on your paper, the ends are the high, and they are more.
Yeah, because you know the N terminal and C terminal are most flexible part of the protein.
Thank you, sir. Okay.
So here, like the residue wise plot. Actually, I'm very sorry for the slow, Okay, so this is the residue, as I told you, like this RES flag will give you the legend of residue. So that is the difference. So here is the RMSF plot. You can plot it like that, and we can calculate the gyration radius. Okay, I just want to show you the beta factor, how you will calculate the beta factor. So again, as I told you, like you have so many things in the flags. So you just have to use the correct one. Okay. So here, okay. So with the OQ, OQ flag, you can have a PDB that is containing the beta factors. So from there, you can take this PDB, and this is the average PDB from the whole, trajectory. So you will get only one PDB structure, and you can color it, and you can get an idea that okay, which part of your protein is flexible and which part is more stable. So from here you can present it. So maybe you can find one of my paper. Actually, I did it in my master's. So there, actually, what I did, like this was a transmembrane protein, and we did simulation. And one part of the, there is 5 domain, and one domain was really very flexible one. So we just wanted to say that, okay, this part is flexible. For that, we calculate the beta factor, and we present it like that. So maybe you can go through my paper and you can see that. Okay, so now we will go for the radius of gyration. Minus TPR and minus here also again, it's up to you what you're gonna choose. Like I choose the backbone. So here you will get the the RG plot, and you can just plot it and have the near publication. Okay, so I just this all about the classical simulation, and there is ton of analysis. You can just Google it and you can find it. As I told you, like there is so many commands are there. Like you can calculate the J coupling, we can calculate the chemical seed, whatever. So you can do, and with the command you can perform this analysis basically. So I just want to say a little bit about the enhanced sampling. Like in this tutorial, we have like there are so many other kind of problem they have addressed. So you can also do that. Like you have membrane protein, so you can follow this kind of tutorial, or you can generate your
Yes, I think Amar is having some question.
Yes, yeah.
I think
Sorry,
network connection is slow, I think. Can you type the question, Amar?
Sorry, we can't hear you.
Yes, I am muting him.
Hello.
Amar, could you please repeat the question? Or else you can type in the chat box. I think you are not audible. Your connection is low, I think. Okay, Krishna, you continue. No, you have some problem, network issue, Amar. You can type it in the chat window. Okay, Krishna, you continue. I'll ask him to type the question in chat.
Okay, so if you have like lipid, the bilayer, lipid bilayer and membrane protein, so you can generate your membrane using there is another one called Charm GUI. So here also you can generate lot of thing. like input generator. No, sorry. There's so actually these people, they change every time. So actually, I didn't use it for the long time, but there is input generator was individual input. Yeah, from here you can get the all kind of lipids, because in the Lampool tutorial there is only certain kind of lipid molecule there. So here you can have all the lipids, most of the lipid you can find here, and also their parameters. So from here you can download, and you can make your simulation. Also they have like I mean, they have one server called CharmGUI server, where you can also make all this thing. Actually, I couldn't find here, or maybe they need some kind of login, because initially it was in here. So maybe you can just Google it and just check it out. This is really very useful website where you can get a number of things done. And if you are working with IDP, just be careful with your force field, because all these force field we have discussed, these are for the soluble protein, and for the membrane protein. But for the IDP, the force field is really very crucial. So be careful with when you are doing the simulation. So I can show you one of the graph. This is like the graph like we did like 2 microsecond of simulation, where you can see this is the IDP simulation, where you can see this is the fluctuation in the phosphorylation. This is the, in a post-translation modification case. This is the apo protein. Here you can see this is somewhat linear, but in that after some 1500 nanosecond, again there is something happened to the system, and again it is going back to the initial one. But here you can see the fluctuations. So these are like this kind of plot you will get when you are working with the IDP or the classical MD simulation. So here, this where from the 750 to 2 microsecond, my system is collapsed. Not collapsed the proper way. This is stuck in some local minima. So this is the meaning of getting this kind of plot. So you never know in which nanosecond and which microsecond you will get such kind of plot. So this I just want to tell you that for the folded protein, it is fine to have 500 nanosecond. You will get the sampling and your system will converge. But if you are working with IDP, so you never know. This will be really very flexible, and you have to correlate your trajectory with the experimental data. So we basically correlate our data with the experiment. So we have the idea. And another thing I want to tell about that, if you are running some kind of simulation like here we have stuck in some local minima. So classical simulation is not enough for my purpose of study. So for that, we have to do some specialized kind of simulation, like some metadynamics, and here how to choose the proper parameters, like which factor I should use for the biasing of my system. That is really very crucial, because there are, if you go to the metadynamics side, this is the plumed package. If you want to do some metadynamics at that time, you have to use some another this plumed package. This is really very useful one, and you can install it in your system along with the Gromax and Umber, whatever tool you are using. So here you can see the CV. CV means the collective variable, the biasing factor. So if you go to the CV, so you can see there are number of CV which are available for the biasing of the system. So here you can see that a lot of CV has been developed. Even you can use some experimental factor like J-coupling, freight, or NOE. You can, and also SATs. Again, RDC is there. PRE also, they are really very useful one for the NMR you get. So these are the thing you can bias your system, and like so basically you have to know it, which one is useful for your system. So there is no certain such kind of rule to know the exact parameters. So for that, what people basically do, the Stanford University Pandal Lab, they have given some hidden Markov way that you can use some kind of hidden Markov approach to get the proper CV. Also recently, one of my colleague and he is developed one way, like what they called, just forget the proper some kind of network thing. I can share the paper with you if you like, if you are interested. And from there you can have the idea, like with the network, like if you know that these are the factors, like some initial study, like initial classical simulation you can do, and from there you will calculate some kind of like these parameters, and from these parameters you can give to this and cluster them, like using k-mean cluster. They found that k-mean cluster is really very useful in that case. So with k-mean cluster, they just cluster it, and they found the best parameter for that for your particular kind of simulation from your trajectory. From there you can choose which parameter I will take for the biasing of the system. So you can bias the system with this collective variable, and like from like I told you, like after 2 microseconds also I didn't find the converge. So I can bias my system, and maybe I will achieve the global minimum. And there is really very nice tutorial over here, so you can follow this tutorial, and also you can talk to the developer. They are really very kind. Some of my colleagues are the developers, so you can talk to them, and you can ask any question, they will really helpful. And also there is very useful tutorial over here, like hard doc. This is one of my supervisor colleague, like Bonvin, he developed this hard doc, and they have like really very interesting like thing, like if you want to dock your protein with another protein, like protein interaction study. If I mean last day someone is asked, so that's why I'm covering this one. So you can also do some protein docking using this hard dock tool, and you can go for the study. So here also they prepare some tutorial, and this is really very useful tutorial of my colleagues. He wrote it, so you can go through this tutorial. It's really very user friendly, and if you have any problem, you can write to him, and he can answer. So I think,
I think one question from Amar
yeah.
is asking how to calculate average RMSD or standard deviation.
So you can just take, this this information, and you can plot it in the Excel. So there is like the similar way you plot the average or something for your experimental study. So this is nothing like not an issue.
Yes, Sudeep.
Hello.
Yeah, Sudeep, you can.
Yeah. So am I audible?
Yes,
Yeah.
yes.
Yeah, sir. So I just wanted to let you know that I had been using Desmond for molecular dynamics simulations.
Okay.
Can you just give me a brief introduction or a brief description with respect to NP gamma T, what I find in assemble function? So can you just give me a brief description with respect to that?
NP gamma. So, sorry,
So it is NP gamma T. So I have been working with some of the proteins, oxidoreductase proteins for mucus hypersecretion. Okay, so in that, what used to happen is while I was going for the simulation purposes, I just found out that automatically the system of the Schrodinger, it identifies that assemble function to NP gamma T. So I was quite confused with respect to that particular aspect. So what actually it does?
actually, I will apologize because I don't use Desmond, and I have not heard about this term. Sorry, I think. So maybe some other expert, they can comment on this. I really don't know because I don't use Desmond, and I don't know. And from the theory point of view, I think I never heard. This term.
Actually, NP gamma T is constant, and NPT is the constant pressure, temperature, and the number of molecules.
Yeah.
And NP gamma T, as far as I remember, is constant pressure and as well as the surface tension of the molecule, surface tension of the surrounding solvent. So it must have something to relate. I mean, I am just guessing, an abrupt guess. I mean, that must have something to relate to the properties of the liquid or the surrounding liquid, maybe.
Okay.
I'm not so sure.
Sure, sir. Yeah, no problem. Yes. Thank you.
Okay, thank you, Pratibha.
Yeah.
Okay, and for the previous question, in the RMSD average calculation, as Krishna told, I will just explore that answer. You have to just copy these coordinates from the XVG file into any file like in which you can calculate the average. You have to just select that column and then see in the below window of that Excel. Then you can see there that okay, average is this one, standard deviation is this one, and this is the sum, and this is the average. So that's how you can calculate the average of RMSD or RMSF or any other thing.
Yes, Rohit.
Thank you.
Yeah, Karan ask.
Yes, sir. I asked in the morning session one question. That was, sir. So sir told that will be addressed in the next session.
Okay.
For changing the parameters to solvent to other solvent, in which file we need to make the changes? Can you shed some light on that?
Yes.
Okay, so for the solvent, actually, I have already shown you that in the topology file, actually, you have to change it. So here you will include your solvent information. So that is solve your problem.
In the same like it is written in the like semicolon input topology.
Like not the semicolon is the comment.
Comment one. Yes.
Comment one. You have to like has include, then in the this exclamation. This how it's called. Here you just put the ITP file. So that's okay. If that this ITP file is inside the local, this working directory, so you don't need this force field trajectory, just ITP. So that will be fine.
And sir, I have one more question.
Yep.
Like if if we want to, like in the initial step when we download the PDB and extract all the water to clean the PDB structure so that the crystalline water goes. But if we want to keep the water that are associated with the active site for the catalytic activity, how we can do that, sir?
Okay, so actually you have to change the parameter as well as in the crystallized water, because the problem is, you know, the Gromax and the force field, they have certain type of atom type. So basically here you are changing the you are changing the parameterized water. So if you want to keep it, so maybe you can develop the parameters by your own in the scope of the force field, so that you can keep it as it is. Or there is another way, like you can fix the coordinate of the, you just know the coordinate of the, you know, this your crystalline water, what is really very useful. So you can just put the same in the same coordinate, you can put the your parameterized water. So that can help.
So can you demonstrate us with that?
Actually,
if it is possible, if it is possible.
So actually now I don't have any protein here, so, and actually I can't right now, so it will take time. So I'm sorry. Maybe you can just write to me in my email and we can discuss about thing.
Sure, sir.
Yes, Krishna.
So
is it some more you have to show me?
So I think I have completed all the things. So if anyone have a question, we can discuss, or maybe we can conclude.
Participants, you can who is having questions can ask Krishnan.
Okay.
Yes,
yeah, I have one question from you, sir. Actually, we have one session from 7:30 p.m. to 10 p.m. But I have not, I didn't get any YouTube live link actually. So is this session will continue from 7:30?
Yes. 7:30. We'll be sharing Zoom link again.
Okay.
Yeah,
So
as per
in
the schedule
this,
it goes. As per the schedule it goes.
Okay, so in this Zoom link we can join that meeting?
Yeah, it's a recurring link. You can join at any time according to the schedule. Okay. And also I will be sending the notice before the start of the session.
Okay, sir. But I didn't get any YouTube link. So can you say
Anil Panwar, sir, why? Okay. You can better join in the Zoom. Why you need the YouTube link?
Okay. Yeah.
Sir.
Thank you, sir.
If you want, I can give.
Okay.
No problem. Yes. For the during session, I have mentioned some of the tools you need to install. That is the Miniconda. I think it is OS compatible, Windows or Linux or Mac, whatever it is. It is. I think it is compatible in all the OSs. What, Rohit?
Yes, sir. Actually, Anaconda or Miniconda? Miniconda. Okay, I heard about Anaconda. That is a Python editor, actually.
Yes. I also mentioned 3.7. If you go to the link, it will direct to the Conda where you can install, you can download and install easily. And also I have added one video how to install that. And you can also find ample of videos in the YouTube how to install Miniconda and Python 3.7 on Windows 10.
Okay. Thank you, sir.
Because during 7:30 to 10 p.m. we have first guest lecture by Holiang.
Yeah.
Followed by this Chanin Nant Sanamat.
Yes.
As he's a foreign reviewer, he will go somewhat fast.
Okay.
You can practice by seeing through the video only.
Okay.
We'll get ready. Yes, that's the thing I want to communicate. Just can we close the session, Krishna?
Yes.
Because participants again have to. Yes.
Yeah, sure. No problem. Okay, yes, thank you.
Again, participants have join again.
Okay.
And anyhow, I will be sharing the link. This recorded videos, everything. No problem. Karan, I will be sharing the links. You can practice it out. Okay. Thank you.
Okay.
Thank you.